Да, если можно. Ага, хорошо, все, работает. Okay, so today we shall be talking about, so today will be maybe most technical involved lecture. I'm sorry for this, but just several times when I have read the similar courses, I have tried to avoid these technicalities. I have looked in many books, but I realized that so far it is, at least from my point of view, it is hard to simplify anything. And so I think quite a lot of people just thought of this and...
What's the Russian translation for technically involved?
Ну, сложные, технически сложные. Да, ну, в смысле, ну да, это просто сложное. Доказательство сложное, техническое. Вот, и как бы ничего с этим не поделаешь. Ну да ладно. Вот, so today we shall be speaking about just our aim, which will be rather long. So just conjugacy of maximal tori and conjugacy and the existence. Yeah.
Last time we were talking about solvable groups and the exact sequence and the
Yeah, we shall recall.
exact sequence. And you said that this time we will prove that it is
Yeah. So
about that.
yeah. So we shall be speaking about conjugacy and existence of maximal tori. So and today we shall be speaking about solvable groups. And so here you have, so here there is, we can speak briefly, since we already have the theorem in our hands, the Borel fixed point theorem, then we can easily reduce to solvable case. Yeah, so the theorem that we are going to prove is the following, so that so G is connected. So well, G is algebraic group, affine algebraic group. Then over algebraically closed field. Actually, this theorem just works over arbitrary field, but there it is, one should discuss in which, more specifically, what one should mean when you are talking, when he is talking about conjugations. So then maximal tori are conjugated. And given given a maximal tori T maximal torus and S any subtorus SO meaning that S is isomorphic to just some product of multiplicative groups, so there exists element G such that G as G inverse belongs to S, to T. And of course, yes, so this proof is will be via reduction, just via reduction to the solvable case. And this will be more or less evident because here we have Borel subgroup. So take Borel subgroup. So it is so maximal solvable, yeah? Maximal connected solvable.
It's not solvable case, it's global case.
It's global case, yeah.
This theorem, first part of this are about conjugated tori, and the second.
So the second is just first says first part is a particular case of the second. So conjugated means that there is a given two toruses, you can choose a G such that this will be the subset of the.
Modular first says only that any subtorus is contained in some maximal.
Yes, yes, yeah. So second gives you that any for any subtorus, you can find a maximal torus containing it.
Why does the first part?
The first is just the direct corollary of the second. Because if you have two toruses, then you can find the element such that the G as G inverse.
It's contained and still maximal.
By the word are conjugated, I mean that there exists some G's such that G as G inverse sits in T. It is just
Not sits in, but equals to.
equals to.
So S
Maybe you are asking about dimensions, but this, I mean, so if given T and T1, so there exists G such that G inverse sits in T1, and there exists G tilde such that G tilde T1 G tilde inverse sits in T. Yeah, so this means that their dimensions, so in particular this means that dimension of T1 is equal to dimension of G tilde T1 G tilde inverse is less or equal than dimension of T. And the same tells you that dimension of T here is less or equal than dimension of T1, so that gives you equality of the dimensions, and so since they are connected, they coincide.
So do you mean that if I choose my favorite torus, then every subtorus in any other group, maybe it's of the same dimension as T, maybe it's less, but it can be.
But if it is maximal, yes, it can be moved by isomorphism to your given torus. But if you have two maximal ones, one can be moved in the other, and the other can be moved in the first one. So it's definitely they have the same dimensions because they have you have equality of dimensions. So that's why they coincide. Yeah, sorry, I just didn't understand why you were asking this. So yeah, so this yeah, so take the Borel subgroup. Maximal, which is maximal solvable subgroup, and of course we had the theorem for so by Lie theorem, yeah, so by Borel fixed point theorem. Yeah, so notice that S at T is solvable. Yeah, so since T is solvable, then there exists some element G such that S or T doesn't matter. I mean, just for the proof. Then you can move G, T, G inverse to B. Or if you are speaking about S, you can just move it by H, by some other element of H. So you can move both toruses to B, and then you can argue via so we shall spend some time to prove this for solvable case. Yes, so this puts, so by changing T, by putting this to be T tilde and this to be S tilde, so then you have two groups inside B. This is connected and solvable. So just we have to prove the statement for our group. Moreover, you see so.
There should be T in the last line, yeah? Is tilde is H as H T H minus 1.
No, I mean that for you can. So we're interested about S and T. Yeah, so you can by conjugation you can move T to B and the S to B. Yeah, so both of them can be moved to some solvable group, and then you can walk there. So moreover, remark.
Is it really by fixed point?
Yes, because this is in order to do this, you have to consider action. I mean, there is a corollary of fixed point theorem, yes, so that you can consider action of T on G mod B. And so the fixed point here gives you the element which you should, by which you are conjugating T.
Just find the time solvable lies somewhere.
So yeah, so it is the fact that any solvable subgroup lives in some maximal solvable subgroup. But this is I mean, if you want to speak about given. So the problem is that you want to put both toruses in the same B.
Yes, but Borel's subgroup are conjugated.
Yes, but in order to use this fact, I want to refer this to the package, of fixed point theorem. So this was corollary of fixed point theorem. So remark that if T is maximal in B, then of course T is maximal in G. Yeah? Maximal torus in G. So this is simply because any maximal torus. So since any maximal torus in G can be conjugated to the torus. So this is the remark and corollary if you know about everything about solvable groups. Yeah? So that maximal torus in G can be conjugated to the torus, to subtorus of B.
Why S tilde lies in T tilde?
I know, no. This is just reduction. I mean, you are just putting that you had the proper. So you had the two not related toruses in G. Yeah. So I reduced this to two not related toruses in B. But then I will spend about a lecture or a lecture and a half to prove this for B.
Okay,
it's completely non-trivial for B. But this, I'm saying that, so I start with this kind of thing because so we shall spend too much efforts, but you will be, so you will think that we are doing this in very particular case and we're doing this for nothing. No, we shall be doing this specifically for general theorem, but it is very easy to reduce it to our particular case. Okay? So the next topic is, so also there is a remark. So this is when you're speaking about the toruses of, so if you are speaking about tori in compact groups, in compact Lie groups, so when speaking about tori, so tori T, which is which is maximal connected abelian group. So if you have such a subgroup and this is compact group, so just setting of Lie theory over, so just then you can think of the analog of this situation. So this is just compact group. And here you also can ask questions that about conjugacy of such tori, and they are also conjugate in this setting. And in order to prove some facts here, so one chooses so a basic idea to choose the element T in torus, such that the closure of its powers, so it is just equal to T. Yeah? And this is just, I mean, this is just easy. So since this is just R n modulo Z n, this is just a generic irrational element. Yeah? So irrational element in any axis. Yeah. So this just yeah. So element with irrational coordinates. Element with actually with one irrational coordinate. Yeah. So at least not one, so with all irrational coordinates. Yeah. So this will be the element of infinite order, and moreover, it will be dense in the torus. And as we have, as it was noted on previous lecture by one of the listeners, that it's impossible to find such element if you change the closure for the Zariski closure. It's not possible to find such element, for example, for finite fields. Yeah, because because when you the fields in positive characteristics, but for example, you can take the finite field and take its algebraic extension, so algebraic closure. But then if you fix some element, it will be defined over the finite field. And over this finite field, you have finite number of elements. And so all powers of this element will be defined over this fixed field. And over the fixed field, there is only a finite number of points on any affine variety. So this is impossible to do it. I was saying about the closure. Yes, so the closure is just the torus. So just it is impossible in algebraic setting for for FP closure, for example. But there is some substitute. So substitute is choosing the element. So so suppose now T sits inside algebraic group G. Yeah? So then there exists. The substitute will be theorem or proposition. So proposition. So assume you have T that maximal torus, any torus in a affine algebraic group. Then I claim that there exists an element, and the analog of dense element is so how one can use it, for example. Yes, so in order to recover T, one just says that you are picking up elements that commute with T. Yes, so just T consists, so here T consists of elements that commute with with T. So you, if, for example, when you're speaking about maximal tori, then you can think of the corresponding.
I just think that elements in torus commute.
Yes, this is nothing. I mean, it's not argument.
It's not that our
yeah.
torus is all elements that commute with.
Yes, I do not say this. Yes, so the claim is that centralizer of. So you can consider, so this element behaves generically with respect to the property of commuting. So the centralizer of this element in G is equal, so such that is equal to the centralizer of the whole torus. So in order to check that the element belongs to the centralizer, you have to check this only for one element. So that's the claim. You will prove. Yes, it is just. I was just explaining why I'm bothering about this statement.
And we are still in SPR. We are still in finite.
No, it is just. So this is. Yeah, so this is just for k equal to k bar. Yeah? So because a priori, so so it can happen that the element is too small. So the proof is the following. So note that this can be proved in notice that T sits in G, and this is some group of GLV. Yeah? So of course this can be proved. So it is sufficient to prove when G is equal to GLV. So indeed, if you put this to be G tilde, so that you have the property that from this fact it follows that the centralizer of G and T is just intersecting this with G. Yeah? Yeah, so the idea is now to reduce this just for the linear group. Yeah? And when you're speaking about linear group, then the situation is becomes a little bit easier, because now you have representation. Now T looks, so T sits inside of GLV. Yeah? And now you can decompose. Now T can be diagonalized. So it can be put into the set of diagonal matrices of V. And this means that you have the corresponding basis. So you have the composition. So just choose the corresponding basis in V. Yeah, so this is basis in V. So.
Can you remind what it can be present in the generalizable? They are all semi-simple for some reason.
Yes, so this the group itself. So the group G. I mean, if it is isomorphic to GM, you can just put it. So they're semi-simple just for the trivial reason, because you can put them diagonally via the components GM, and then you use that. Yeah, so that it consists of semi-simple elements, and then you use that important fact that it can be diagonalized in any given representation. Okay, so so this is a basis, and you are given an element of T that you may think that it multiplies the vector by the just by some fixed number, but this number can be viewed as a function on T, so as algebraic function on T. So this is a character that maps the torus to K multiplicative group. So this is a regular function. So the claim is that you look at this decomposition. Yeah, so you can combine these vectors in the vector space with the same characters. Yes, so just you put Vi to be just the subspace of V such that action of torus on V is via this character, and these vectors from different vector spaces are linear independent, so you have the composition of V into this direct sum. Yeah? For any t, yeah, so otherwise. So I'm not claiming anything about given element yet. So now I'm just speaking about all torus. So yeah, so this tells you that V is decomposed. Yeah, so this of course are subsets, and knowing that it is diagonalized, then you know that this just vectors coinciding with V, and they are not intersecting. So you have this direct sum decomposition. Yeah? And in general, there is inclusion of this in general. There is, of course, inclusion of this, but since T is diagonalizable, we have equality. Yeah? So, so this is how you derive it. Yeah? So this, if you have this kind of decomposition, notice that the torus acts on these vector spaces by different numbers, so by different multiplying by different functions. But for some elements, of T. They can act by the same, it can happen, that they act by the same numbers on different vectors from, on different vector spaces here and here. Yeah, so it can happen that psi I is equal, psi I of t is equal to psi j of t. Yeah, so this tells you that just t acts on V1, I and Vj by the same character. By the same number, yes, so by the same.
Yes, yes. Because T small one acts here.
Yeah, it just, yeah, by the same space. So, eigenvalue. So, but this can be written simply, so this condition is just vanishing of the character, so you can write it down as this one. Yeah, so just multiplying these characters. And so here I mean just dividing one character by the other. So let me put it like this. So in order that it will be clear what I mean. Just saying that this is equal to 1. So this is just the kernel, so the zero set of this function. So this is by Krull dimension theorem. This is codimension 1 subtorus. Yeah? note that the vanishing of the character is gives you the subtorus, yeah? And this is precisely saying that it is a codimension. Yeah, well, codimension 1D group, yeah, so it is, it's, yeah, so. Okay, so this tells you that, yeah, so let us introduce the singular set. So this is a union of, so let us call it Dij. So the union.
What if xi and xj are equal characters?
Yeah, no, so I have taken this decomposition just by this definition, so in order that they're different. Yeah? So just choose, so these characters.
Okay, so.
Yeah.
So codimension 1 is because it's an algebraic function.
Yeah, it is just a regular function. So on one hand, it is the group, yes, so it is as the subgroup, the kernel of homomorphism is the subgroup. It is the group, but it is codimension 1 because it is just one non-trivial function gives you one non-trivial, non-invertible function gives you precisely. This is non-invertible because I'm substituting 1.
It's the code dimension. You say that it's called from dimension theorem, exactly that.
That one equation gives you the subset of codimension 1. Okay? So Krull principal ideal theorem. Yeah? So this. Yeah, so then you can consider T singular, so this is just the kernel of this character. So this is a union of Dij. Yeah?
And it's non-invertible function only in case that we have this time T small.
Yes, it can, I'm.
Part that it can happen.
Yeah. So this. Yeah. So this is just the union of this group, and you see that it is not full subset. So there are a finite number of indices, and this is not. So this is not equal to T for dimension reasons. Yes. So for dimension reasons. Yeah, because this are finite number of subsets, finite number of subsets of codimension 1. Yeah. Notice that Krull theorem says that all connected components, if you have one equation, it can define the instance with different connected components, but all connected components have the corresponding dimension. Yeah? And now you just do the following. So you will notice that if G belongs to normalizer of the torus, it permutes, then G permutes. Будьте здоровы. So permutes VIs, yeah? And if it belongs to centralizer, then it fixes this. So if G belongs to the centralizer, then G fixes Huh?
Are you going to explain why this happens?
First we did for a million times. Yes, so this, if V is just the element that TV is just chi I of TV, yes, so then you are just applying G to T to GV. So this is just saying that this is G inverse T G, yeah, times V. But now this is a new element, so this is an element of torus. So this, since it is in the normalizer, this is an element of torus, so it acts like the given character, but applied to different chi. Yeah? So you see that this character is this as a function, or so this new character of t. So this can be viewed as a new character of t, defined as simply evaluating old character on this element. And of course, if G centralizes, so if G belongs to the centralizer of torus, yeah, so these characters are equal. Yeah, so chi tilde of t is just equal to chi of t, yeah, because this is 1. Yeah. Okay, so this tells you that, yeah, so since these spaces are different, and so this means that the space with the character, some given character, maps to the space with this twisted character. And since this decomposition in the sum is direct, the only thing that can happen that one factor will map to the other. And just by the inverse, it should map to if you have one factor Vi that maps to Vj, so by G, then of course G inverse maps it in the inverse direction, and you put this as a subset here and this as a subset here. So they're equal, so this means that they should be permuted. And if the element is central, you are just fixing one element. So this tells you that if G centralizes, if the element G is the centralizer, so G fixes this decomposition. And this and the same is for function, and the same is for element. So if you have notice also that since our torus is just, so the action of torus is just multiplication of each element here by the scalar, yeah, so if, so in other direction, so just if you have element of G that, of GLV, that G belongs to centralizer of T, then G fixes, so G maps all VI's to, so fixes decomposition, meaning that G maps VI to itself. Yeah? And vice versa, if G acts maps Vi to itself, so since just action of T is just is a multiplication by the scalar by chi I of T, then G commutes with just for any I. Yeah? So G commutes with T. And the same can be done for the whole torus, thinking of this as the functions. Or you may just apply it to one element. Yeah? So if you have just the same holds for t, for element t, that acts with different, so that acts on vi by lambda by multiplication of by lambda I, such that lambda I is not equal to lambda j. Yes? So this means that the centralizer in GLV of this element t is just the product of the corresponding GLVs. Yeah? And here I mean the same. Yeah? So this, and the same for such t. Yeah? And the same, you do the same calculation for the whole torus from the previous remark, and you get also that it is the same subgroup. Yeah? So this theorem holds for the element which is not anti-singular. Yeah? So this just we did this calculation for the element which is not anti-singular, and you see that this are equal. Yeah? Okay. Да.
Мы пользовались тем, что он не лежит здесь.
Ну, если просто смотрите, тут чем мы пользовались? Тем, что элемент лежит в не лежит в T-сингула, только тогда на каждом VI там у вас разные умножения на разные лямбда. Но как раз вот мы пользовались тем, что если ваша группа нормализует тор, или то же самое нормализует этот элемент, ну, группу, порожденную этим элементом, она также должна нормализовать это разложение. Ну, то есть каждый элемент виита переводить в себя. Но это значит, что, ну и в то же время она может действовать любым оператором на каждом из виитах, да, переводя вииты в себя. Тогда это просто элемент вот такого вида. Ну, как бы вот этим мы пользовались. Что мы можем применить то же самое утверждение, что к группе к самому тору Т, что к группе порожденному элементу, да, одним элементом. Что если элемент централизуется, то тогда он сохраняет разложение.
То есть если бы они были равны, какие-то два характера,
то тогда вот эти вот слагаемые лежали бы в большей группе, ну, что вот эти два слагаемых лежали бы в группе, которая может любой вектор отсюда, ну, в смысле сумму переводить в сумму. Да? Так мы каждое слагаемое переводим в каждое слагаемое, а так сумма переводится в сумму.
Да, хорошо. А вот
то есть, как бы, вот смотрите, там, где, ну, грубо говоря, если мы запишем это в матрицу, то, ну, вот это, тут есть, ну, вот мы их распишем вот так блоками по характерам, то вот первый блок соответствует V1, второй блок V2 и так далее. Ну, как-то нет. Ну, вот как раз в этом-то и point. То есть...
Изначально какие-то тоже, как V1, V2.
Нет, но они... So there was a question that there was a conjecture that this were one-dimensional spaces, but notice that when you're speaking about bases, they're of course one-dimensional. But then you are picking up the elements, so you look how T acts on them. So you act by EI by different functions. But these functions can coincide for some elements. So you combine them in block where the functions are equal. Yeah? So I define Vi to be the set of vectors that are the action of t on this vector is given by the same scalar.
So that n and that n are
Different, yeah.
Even and small t is any non-singular element.
And the t here is non-singular element. Yeah? So taking non-singular element, you see that there are eigenvalues on different vector spaces, which are just are all different.
And we proved that general element have this property.
Yeah, we proved that this condition is just the complement to codimension one subset. The union of finite union of codimension one subsets. Okay?
We prove that I understand why if T is subgroup generated by T, then it's clear. But why it's called for?
This one, the centralizer of the element is equal to the centralizer of the powers of the group generated by the element.
Yeah, but why we may assume that it's dense?
Нет, нет, здесь мы ничего, нет, ну просто,
What is big T?
нет, нет, просто Т это наш тор, который вот действовал так. Ну, как бы вот с помощью вот этих характеров. А Т это общий элемент его, ну, как бы достаточно общий, для которого вот эти вот...
So we
yeah.
just conclude equality because they are both.
Because this side is equal, yeah. Just, so this is our calculation, yeah.
То есть, типа, если надо стабилизировать, нормализировать,
Нет, ну вам нужно утверждение такое, что если есть разложение, которое каноническое, с разными собственными значениями, которые переходят в себя, то его централизатор это и есть вот эта группа. So the claim that
вопрос, что такое Z от T большого? В смысле, что такое?
централизатор.
Ну, это то, что при сближении входят элементы под группы в элементы под группы.
Нет, это нормализатор. Централизатор это коммутирующие элементы, да.
Совсем и
Мгм. Хорошо.
Where did we use that it is torus?
На самом деле, нигде, да. Но это, в смысле? Не, это где спрашивается где мы использовали, что это торус, а не диагональная, а не D-группа. So there was a question where we used that it is torus but not a D group, so we didn't use that it is D group, that it is torus. We used that it is just D group. Yeah. So thank you for this remark. Yeah. Right.
Is the torus abelian?
Hmm?
Is the torus abelian?
What?
You said the torus T consists of elements that commute with T. What is it?
Yes. So the centralizer. Yeah.
That's right.
This one. You mean?
I mean the upper sentence.
It is just remark that all elements of the torus, since it is commutative, commute with any element, and you can try to. It was just the remark how you can use that the element which is dense inside your maximal torus, that you can recover maximal torus as the set of elements that are commuting with your given element. It is just nothing. It is just the saying that the T in the group T is just its centralizer. So I mean there is an argument in compact group that if you have T and if it is so that centralizer of T is equal to T. Yeah, so just 4 compact groups. And the idea is just that you can take, if not, then you can take an element Z from this centralizer and generate a bigger abelian group by Z and T. And then this will be a larger abelian group, subgroup. You can take its closure, and this will be the just in compact group, this will be the bigger torus that contains T. This was, I mean, this was just
the example of the group which is not the torus.
just multiply by any finite group.
So it's connected.
Of
of zero is always a torus, but
connected but
is connected.
yes, and we proved it because
I just whatever.
yeah, okay.
Could you repeat what is the definition of normalizing in space?
Of what?
Of normalizing.
Sure. Just it is just the set of elements of G such that G inverse sits inside T. Sorry.
So the centralizer is a subset of the normalizer.
Yes. And for torus we proved so for tori we proved actually for D groups we proved that connected components of normalizer and centralizer are equal. So they are not far from each other. Yeah.
I also want to ask about T singular. It depends on the vector space radius.
Yeah, it depends on the embedding. Yeah, so that this is not. I mean, from the viewpoint of toruses, there is it doesn't appear if you just take abstract torus, the product of GMs. I mean, it is nothing. Yes, so but if you are picking up, if you are embedding this torus in some group G, or more generally in the representation of GLV, then this you have this kind of decomposition. Now the characters appear, so you can define this subset of T. So this is the part of the data that T was embedded as in GLV, in general linear group.
And for different vector spaces V, even the number of components.
What?
For different vector spaces V, the number of
Yeah, it can happen. I mean, when you're speaking about GM, you are just free to choose just this V to be. I mean, if you're just speaking about this vector spaces, you are free of the product of GMs. You are free to choose any collection of functions, and you are free to choose the spaces of arbitrary dimension. Yeah? But of course, this T singular depends only on the characters that appear here. Yeah? Just for trivial reasons.
And
Okay. So if you will have questions, you can ask them later.
But in the same time, this torus acts on itself like another joint.
The torus acts trivial then. I mean,
But it permutes the components of
the torus can act only by conjugations. I mean, so the question, which action of torus do you mean? So if you mean conjugations, since T is abelian, it does nothing. Yeah? So if you are thinking about on the characters, this action comes from the conjugation, and in order to have this conjugation non-trivial, so this should be act non-trivially on torus by the conjugation, and this, of course, is not the case. But if you think of normalizer, then normalizer really permutes that. Yeah, so that it permutes the singular. So so the remark. So remark since. So the normalizer. So this was a good question actually. So since normalizer permutes this VIs, then it permutes the action of the normalizer on the set of characters. Via just n inverse T n. Permutes this collection, this given collection of characters, the collection of characters, which is chosen here. And this just means that it permutes this Dij. Yeah. So the groups introduced here, yeah, because it's just permutes characters. So in particular, the situation that can be applied. So just this is a. So now we actually can introduce the roots. So roots. So if you have T that sits in G, yeah, so you have an action, so you have a natural representation of G on its algebra, so via a joint representation. And then this gives you, so the torus, the action of just this, the restriction of this representation. So just looking at this as the restriction of representation to the subgroup, it diagonalizes. Yes, so diagonalizes. So you can just consider the components. So you can decompose G into the direct sum, and of course here there is a natural subset. So here you have so T sits in G, and this is fixed by a joint action of T. So because if you have Lie subalgebra, it is fixed by the action of the subgroup. And and you see that G can be decomposed into the set of fixed points plus the remaining parts. So they are denoted G alpha. So alpha is a character of T. And in this case, they are called roots. Yeah? So in this case, we call them roots. And our group, yes, so the group we are considering here, so as we have noticed,
You raise G alphas,
are just the analogs of VIs, yes, so G.
they are vectors of
Yeah, so
the
the,
injection.
so they are precisely the element xi of G, such that the joint action by T on xi acts by multiplication of this character. Yeah, so alpha of T xi, where alpha of T is the function from T to K star.
So,
So,
the fixed elements are such that lambda is 1.
yes, yeah. So just they are just here the alpha, it's alpha, is a trivial character, and
They do not depend on the choice of the basis.
yeah. So they don't. Yeah. So they don't depend on the choice of the torus. Yes. So and this G alpha don't depend on the choice of the basis because I am not using basis in order to define them. And I just so notice that I have here I have started by picking basis only for to do the following. So you have this VIs are defined without basis. So so this inclusion. So this contains this direct sum. This is because if you look at, because this contains the sum of these spaces, but you know that the vectors with different characters are linear independent. So these guys are the same. But then in order to establish, so we used basis and the diagonalization in order to establish that this thing is equal to this one. Yeah? We used that. So this is the statement without torus. So this is just a statement about linear operators. So a statement about just operators. And here we used that just the action of T on V is diagonalizable. To prove equality. And we prove the equality simply by saying that you can diagonalize and then combine your vectors in these vector spaces. Yeah. So,
Is it true that every root has its own character? Alpha.
I mean, just I mean, alpha is precisely just so we call root just a character. The root is a character of torus. So you just yeah.
Is called not
Yes,
not
yes.
also eigenvectors, but
Yes.
character.
We call alpha root just these characters the roots, and these are root subspaces.
So adjoint action is restricted to the T subalgebra.
Yeah, subgroup.
T,
Or you can, yeah.
T the subalgebra is fixed by
of G. Yeah, because because simply because just you have this kind of inclusion. So if you have element of T, it fixes T. So it fixes T, fixes fixes E, yeah, the unit element. So it fixes tangent space to T, simply because it is M E modulo M E square. And since it acts trivially, it also so T acts also trivially. On T. So this implies that it acts trivially on the algebra of functions. So this just acts trivially on ME modulo ME square. Yeah?
So do you mean that there are marked characters from the marked characters for this maximum torus? Those marked characters.
Yeah. So so this is the general situation when T is realized as the subspace of the just a subgroup of a linear group, or T is realized as the subgroup of G. So in particular, so actually T is so the joint action realizes T just as the group of linear transformations of its Lie algebra. This defines your, so there are many characters, yes, so there is a lattice of characters isomorphic to Z to the power n, where n is k, where k is the dimension of torus. But here you, if you are speaking about fixed subspace, it can be composed only infinite number of collection of subspaces. So only finite number of characters appear here. So this is some fixed collection of characters that is related via this embedding.
So
And
the embedding maybe the embedding defines the roots.
yes, yes. But you can think of this as follows. So if you are speaking about, so this is true for any diagonalizable group. I mean, such this picture is valid for any diagonalizable group. But of course, you can do this picture to be chosen canonically with G, because you know, if you take the group G, you may take some object which is canonically related with G, for example, maximal torus. So this will be, if you know, of course, the theorem on conjugation. So then you know that the character, so you take this group, you take maximal torus, and you get the object which is related with G. Yeah? So this kind of decomposition, it is plugged in the structure of G.
And because maximal torus are conjugate,
Then this can be thought of independent structure that is really the structure of the group. Yeah, sure. Yeah, let us do it. I mean, now it is a good point to do it. Yes. Yes. Okay, we can continue. Yeah, so now I want to speak about one element, one semi-simple element, and orbits of, studying orbits of such elements.
Можно такой вопрос?
Да.
Технически сложная часть началась уже или нет?
К сожалению, нет. Вот сейчас она начнется, вот она только сейчас. Нет, это предыдущая была простая часть. Ага. Она не сложная, она техническая. Это вот как бы есть разница. Ну, как бы то есть просто, ну, это само доказательство, оно просто будет очень длинное, и как бы, и, к сожалению, все, что мне нужно вот, как бы сказать, там будет использоваться, и поэтому...
А доказательство чего?
Доказательство сопряженности максимальных торов в разрешимой группе.
А вы еще не сказали?
Нет, я только свел к разрешимым, а теперь...
Сейчас, а мы доказали, что достаточно для разрешения?
Да.
Алгебраически.
А почему достаточно?
Ну, потому что любые два тора с помощью сопряжений мы знаем, что можно поместить в разрешимую. Ну, а дальше надо найти, дальше надо их сопрячь в разрешимую.
Потом мы сказали о нормализаторе, точнее про централизаторы, и пока не используем.
Да, это так просто. И мы не скоро это используем.
Подождите, то есть на самом деле это для любой группы верно, что...
Про централизаторы, конечно, но...
Не, вот что для любой афины алгебраической существует максимальный торы сопряжены.
Да.
Я думала, для совершенных.
Совершенный. Да. Нет, не для любой сопряжены, в том-то и дело. Ну, как бы, поэтому они и важны, что...
Сейчас.
Просто как... Да.
Мне немного непонятно. Получается, что в любой алгебраической группе максимальные торы сопряжены.
Да, это так. Ну, просто есть, так сказать, ну, есть факты, ну, то есть явления природы, и то, как человек их доказывает. Ну и, к сожалению, факт природы верен для любой группы, но, к сожалению, чтобы его доказать, нужно отдельно проверить его для разрешимых групп. То есть как бы бесплатно он не получается. Ну, как бы вот... И вот сейчас мы будем вот пытаться это сделать. Да.
Можно взять любую конечную группу.
Но там и торов не будет. Да.
Да. То есть умножить ее на кружку.
Ну, на К со звездочкой или что. Да.
И применительно теорему. Максимальный торы.
Но другое дело, что тут нужно быть аккуратным. Ну, так сказать, вот, ну, в смысле, что любая, ну, эта конечная группа должна быть реализована как алгебраическая. Вот это как бы, ну, то есть вот это маленькая тонкость, но она не пустая. То есть если у вас есть группа конечная, то вы не можете просто взять абстрактно конечную группу. Вот вы должны ее уметь реализовывать как алгебраическую группу. Это говорит, ну, например, как бы, ну, у вас есть вложение в Sn, и, ну, there was a question about finite groups. So the thing is that we work not with finite groups abstractly, but finite plus embedding in GLV. Yeah, so we are looking at a finite group as a group with an algebraic structure, but then this can be done as actually one of you just suggested on some of the class that you can put F to the permutation group, for example, via right action of on. So this Sn is just the symmetric group, which is consists of the element n is the number of elements in the group F, and then you are embedding this into action of just permutations of the basis just E1, En, and this embeds the symmetric group in GL and just the corresponding linear group. And so you're thinking of the final group not as abstract group, but with this embedding.
And if we multiply this group by Gn,
yeah, will be diagonalizable. Yeah, there will be D group. Yeah, I mean if it is abelian, if and only if it is abelian. If it's not abelian, then you cannot diagonalize. Yeah.
yes. But then maximal tori correspond to.
But all maximal tori can live only in the connected component. Yeah.
Yes.
So,
So they correspond to elements.
the
Finite group.
no, the finite group acts on them and acts trivially. Yeah. So the maximal tori should be in the corresponding connected component of the unit. Yeah, because it is connected subgroup.
So there is only one.
Yeah, there is only one maximal torus. Yeah. Yeah, so here we're speaking about conjugacy classes of semi-simple elements. So, yeah, so in order to notice that if if you have a remark, if you have so here you have so you want to consider the following problem. So you have to you want to pick up some semi-simple element, and you can consider its orbit. Yeah, so the under conjugations. So this is a subset of G. So the union under G. So orbit, a joint orbit. But the problem here that so of course it also sits in G, and the thing is that the problem is that this joint so there is a unit somewhere, and this joint orbit. So the main point is S here. So this definitely doesn't pass. So E is fixed under conjugation. So definitely a non-trivial orbit doesn't pass from E. But you want to have the property that, so you want, if you want to study tangent spaces, the properties of this varieties. It is convenient to study tangent spaces, but the tangent space to the orbit sits in some point x. So the idea is that you can move to E by considering different maps. So consider just the map from G to itself, GS that maps element of G to G, S, G inverse S. And so the benefit here that you have, if you have unit that maps to the unit under this map, it is the first benefit. So you can consider so this the differential of this set that maps the tangent spaces. It maps the tangent spaces in the unit to the tangent space in the unit. And yeah, sure. And it maps actually the algebra to the algebra. Moreover, if you have H, the subgroup which is in G, which is normalized by S, this maps, so moreover, if you have this orbit, moreover, the properties of this X is closed, so the orbit at the G of S is closed, if and only if its translation, so gamma S of G is closed. Because they are obtained by translation. So the properties of these orbits are the same, just of the orbit and the map of this variety are the same, but the benefit that this has convenient tangent space, and also if you have the group which is normalized by S, then of course, so I claim that gamma S of H is just also sits inside H. Yes, so and the reason for this that you have G. So if you have H S H inverse S inverse, yes, so you see that this is an element of H. So this is a product of two elements of H. Yeah, so since H is normalized. So so you can consider, so if this situation happens, so this at least you know that gamma S of H is contained as in the intersection of gamma S of G intersection with H. Yeah? And this will be used. So how we should use here this thing? So suppose now S is, since S is semi-simple, then you can consider a joint action of G, of S on G, on the Lie algebra. So S is S is thought to be the element of the group. So actually we can think of this that G is just the general setting that we want to have is that S just sits in some GLV. So so general allocation. So just our our aim is to study the following situation. that you have separately the element, and here you have subgroup, and the S normalizes H. S normalizes H. So you have the map of semi-direct product of S and H in GLV. So S is now you have the action of so a joint action of this semi-simple element of G, and as before, you know that it can be decomposed. Yeah. In the sum of the corresponding GI. Yeah, so just eigenspaces. So there is let us decompose it into things. So one is the eigenspace of the vectors fixed by
What's
uh-huh.
f of S? It's a point.
What?
What's f of S? It's a G S.
По-русски спросите, я уже.
Add от S это add G от S.
Это, ну, в смысле, это G просто, извините, это опечатка. В смысле, я разложил G в соответствии с, ну, в соответствии с действием на G.
Потому что S полупростой, так получается?
Да, это из-за того, что S полупростой, вы можете разложить в прямую сумму собственных подпространств. And if you decompose G into this direct sum, of course, here you have, so there is the centralizer of the element S in G, and the Lie algebra of the centralizer. And this is a fixed point, so this set is, so if you take a centralizer of G, the set of elements that commute with G, then clearly this will be, if you think of a joint action, yes, so this will be just the invariant subset via respect of, so here S acts trivially. By fixing all elements, yeah. So by via this joint action, and this means that on the Lie algebra, on the corresponding algebra, S also at S also acts trivially. On the Lie algebra of Z. And moreover, it is also clear that, so that that this map, so you have, so this is precisely just this quotient maps to the variety, to the orbit, to the corresponding orbit. And the thing is just, yeah, so it maps to the corresponding orbit of a joint action of G on S. Yeah. But the problem is that and it actually it maps bijectively, so it maps bijectively But it can happen that this is not isomorphism. So just in characteristic P, in characteristic 0, this implies that if you have, so on the set of points, you have, you can consider the action. So this, on the set of points, this guy maps to the orbit bijectively, yeah, because you have the corresponding map of the cosets. But this, in characteristic 0, this implies that this is this is isomorphism, but in characteristic P, this can be not true. So in characteristic P, this can be not true.
Разве мы вот это многообразие G фактов после GTS, когда мы снабжали структурой многообразия, разве не...
Так мы его снабжали-то не исходя из других соображений, исходя из неданного действия. Вот тут я как бы сказал следующее. Ну, то есть мы вот эту... So there was a question about just considering the structure of algebraic variety on G mod S. Yeah? And the trick that we did is that we have realized G mod H, so for arbitrary H, somewhere in P mod V. And we have realized it in such a way that this embedding is algebraic. So, but this doesn't say that the following, that given x, so suppose you have taken x itself. Yeah? So suppose you have taken a point x. And then you can, of course, so suppose it also happens that so you can consider the the stabilizer of x inside the G. Yeah, so just thinking of this not scheme theoretically, but just the set of elements of G such that Gx is equal to x. So the problem in which is just doesn't arise in characteristic 0, but arises in characteristic P is the following, that this as just so the set of points, so this will be an algebraic group, of course. But then you have the orbit map that maps G to Gx. And it factors, of course, through the stabilizer. But it can happen that still this map, so it will be surjective map. But not necessary, it can happen that it is not injective. Yeah? But it can happen. It is surjective finite map. But it can happen that it is not injective. So this is not isomorphism, and the reason for this that this can be not separable map. Yeah? Happen that it is not separable. Hmm? Yeah. Yeah.
And another question here is that I remember during our construction, H should be an algebraic subgroup, right?
Yeah, even if you think this as an algebraic subgroup, it can happen that this is not this is not isomorphism. I mean this part. But so the problem is that this thing, if you want to just have the isomorphism here, should be just described as a group scheme. And if it so this is precisely the place where you have to define stabilizer, so as some intersection with the graph, and there the intersection will be not the subgroup, but the subgroup scheme. So this actually will tell you that H sits inside the group scheme which is bigger. So from the
Inside what?
the group scheme.
Ah, it's
So it can happen that this has nilpotence. So with nilpotence.
nilpotence in functions. You mean?
Yes. In algebra functions. And this will be precise. So the situation will be precisely the following: that if you have the bigger group, then the quotient will be larger here. So this will be some finite map. So finite, not separable map. And this was one of the instances that we have a difficulty, that we have taken diagonal group, mapped it by the collection of characters, and then I didn't say that it is isomorphism. I have derived something out of this. And this is the same picture that arises here. But
So the orbit can have nilpotence.
Orbit doesn't have nilpotence. The stabilizer, so if you think of stabilizer as the subscheme,
Yeah.
then it is the stabilizer is realized as some intersection just in the some intersection with the graph, yeah, of the action, and of two varieties. But the intersection, if you define the intersection in terms of in algebraic terms, or by the just by saying that, so the best way to define intersection is just say that you take the sum of ideals. But the sum of ideals can be, even if they are radical, can be not radical ideal. Yes, so so the trick is that you are defining this, when you are working algebraically, you have to define the stabilizer as not by radical ideal, and if you do this, you will have isomorphism here. But we are doing it in our setting just by saying that we are taking the reduced part, yes, so that you just kill the nilpotence by factorizing by nil radical. So that's why it is, so here you have, if you take specific action and you take the stabilizer, in characteristic P, you cannot guarantee that it is bijection.
When we factorizing by nil radical.
Ну, в смысле, вот, чтобы перейти от групповой схемы к настоящему стабилизатору, вы должны отфакторизовать алгебру функций по нель-радикалу, да?
А получается групповая схема там, если...
Ну, групповая схема получается, если там есть нильпотенты, но из нее можно сделать группу, да?
Изоморфизм все-таки будет, если мы возьмем
Групповую схему, да, да.
А где возникла H-числовой?
Не, ну в смысле, что вот эта вот штука, ну как бы вот это вот, если я пишу вот так, то это теоретико-множественное определение для любого элемента. Вы это условие можете записать разными способами. Ну как бы можете записать в полиномах. Но когда вы думаете о многообразиях, то вы обычно все-таки берете подмногообразие с приведенной структурой.
Сейчас.
Ну, в смысле, что вы пишете, вы по вот этому условию пишете набор уравнений,
Да.
но как бы после этого выбираете приведенную, радикальный идеал. Но у этого набора уравнений вы берете радикал от этого идеала. Ну, чтобы у вас было соответствие между многообразиями и системами уравнений.
То есть там были какие-то уравнения, которые уже умножены на x, равно x, это единственное вот это уравнение мы написали.
Ну да, просто это значит, что вы можете написать это в терминах координатных функций.
Там типа x квадрат.
Ну, у x есть какие-то координаты, поскольку x лежит в афинном пространстве. И вы можете, грубо говоря, вот это уравнение написать как g на x. Координата g на x равна координате x. Ну, как бы вот так. После этого взять, просто это самое. А можете реализовать вот в виде пересечения с графиком, как мы это обсуждали вот на первых лекциях. Ну и вот это вот пересечение с графиком, оно может быть, не приведено.
То есть h с волной это пересечение с графиком.
Да, h с волной как схема, пересечение с графиком, но вот в терминах идеалов, да, то есть как бы.
А то, что там написано вложение, это как бы теоретика множественное, оно...
Вот это?
Нет.
Вот это в смысле, если у вас, у вас есть морфизм алгебры cat h с волной, фактор, фактор cat h, это cat h с волной, фактор по радикалу, да.
На точках как бы...
По ниль-радикалу. На точках ничего не происходит.
А pullback это...
Да. Не, pullback просто вот эта функция забывается, факторизуется по радикалу. Но дело в том, что если вы считаете значение функции, то, как вы считаете, что значение функции не зависит от ее представителя в ниль-радикале. Да? Потому что значение функции получается так. Вы берете максимальный идеал и берете значение функции, это вы просто функцию берете по модулю этого максимального идеала. Но радикал, ниль-радикал кольца, он лежит в пересечении простых, в частности он лежит в данном максимальном. Поэтому значение функции не зависит от выбора классов нильпотентах. Поэтому вы на уровне значений функций вы не чувствуете, вы не можете почувствовать ваша схема с нильпотентами или без. Потому что, это вы чувствуете только если вы помните об идеале. Хорошо? Но к этому надо... So there was explanation that the value of function doesn't depend on the choice. If you take the function on non-reduced scheme, the value of the function doesn't depend on the choice of... so it doesn't depend on the choice in its quotient via the... In the class module nil radical, just because evaluating the function is just taking this function and taking it mod some maximal ideal, where this maximal ideal corresponds to the point on your variety. But nil radical sits in all maximal ideals. And the spectrum of non-reduced scheme also, and the maximal spectrum is of course the same as for the same reasons that of A mod nil radical. Just because the prime ideals here already contains nil radical.
How do you show that the centralizer of that is an algebraic subgroup?
Yeah, so the centralizer is just algebraic subgroup, so you are writing down this kind of condition for via coordinates. Yeah, so this means that, yeah, so x sits inside AN. So you may think of this as, yeah, so the centralizer is stabilizer. Yeah, so you can write down this definition naively, so saying that the ith coordinate of Gx is equal to just ith coordinate of x. Yeah, so just so the claim is that yeah, so this is what now we know about the centralizer. Yeah, so also if you are working, yeah, so the exercise that, so the exercise is the following. So it is discussion how the joint action is considered in GLV. So if you have in GLV, so for the whole linear group, we have correspondence that this, yeah, so here you have the corresponding Lie algebra, and you can take an element of V, and so you can think of this yeah, so of V, and you can consider the, yeah, so, sorry, I want to speak now about the joint action of, so to consider a joint action of GLV on its Lie algebra. Yeah, by conjugations. Yeah. And here you have an explicit formula. Yeah? So here you just map x. So just GLV is now embedded as the set of invertible open subset in this GLV. So you can think of this. So you can write it down in terms of matrices. Yeah? So the element G acts on some xi via just writing down G xi G inverse. And also you have a joint action, so the action of Lie algebra. So derivative of a joint action. Yeah? So the joint action of G to GL of V. It has a natural derivative, yeah. So the just T of G, which is Lie algebra, it acts on. So if it is phi, so here you have a differential of phi that you apply to xi, and this gives you. Ну, линейное преобразование G. Ну, алгебры Lie G. Ну, в смысле, что G — это векторное пространство. Вы можете рассматривать линейное отображение G в себя.
А почему оно маленькими буквами?
Это типа эндоморфизм.
Ну, это эндоморфизм. Ну, в смысле, это не отвечает на вопрос, почему это эндоморфизмы. Но это традиционно, потому что эндоморфизмы или матрицы — это алгебра Lie G LV.
Почему это сейчас это алгебра Lie G
Не, ну, в смысле, тут, да, почему, да, тут она, конечно, в большие буквы. Ну, а здесь в маленькие, да? Да, спасибо, да, спасибо. Вот, да, и вот это уже не здесь, а вот здесь, да. Ну, нет, тут как раз вот здесь. Ну, в смысле, тут они обратимы, эндоморфизмы — это не изоморфизмы. Вот, соответственно, so here you have this kind of the derivative, and just the derivative of the section, the precise the direct calculation shows that if you just make the set of corresponding this is the direct calculation of differential tells you that it is just the commutant. So if you have eta here, so this is just a commutant of matrices. Yeah? So so here you and the claim here that for a joint action, so you can consider the stabilizer of this action, the stabilizer in GLV. So the stabilizer, so for G equal to so for the group for the group G equal to GLV, yeah? So you can compare the centralizer. So here you can define centralizer of the element in the Lie algebra. So this is the set of elements eta such that in the Lie algebra such that they commute with eta with psi. Yeah? So then you have so you can take the centralizer of Xi and compare it with the centralizer in GLV. So the claim is that Lie algebra, so exactly, so this kind of direct formulas show you that Lie algebra of this group is equal to this Lie algebra of the centralizer. Yeah? So for an element.
What is the last? What is Lie algebra of centralizer equals what?
Lie algebra. So Lie algebra of centralizer of the element via joint action is equal to the sub-algebra defined as the bracket is equal to 0. Just so the problem is that for NXI. Yeah? So so the problem is that since you have this kind of property, so that when you're speaking about characteristic 0, or you are just considering the case of Lie groups and the Lie algebra, so you are considering real manifold. Then here you have isomorphism, and this implies that just this and this group, so this Lie algebras are the same. So in characteristic P, it can happen that these objects are different. And this is precisely, well, technically the most non-trivial part in this proof. Да.
Не алгебраически просто вычисление, то, что...
Не, вот сейчас, ну, когда вы вот это пишете, это алгебраическое вычисление.
Ну да.
Но проблема в том, когда вы, ну, вообще говоря, вот это ожидаемо, что вот это верно для любой подгруппы, не только для GLV. Ну, то есть для групп Ли или в характеристике 0, то это верно вообще, ну, без всяких предположений. То есть, ну, не для GLV, а для любой группы.
Ага, то есть вот это,
И вот,
оно верно всегда для GLV?
да, наверное, всегда для GLV, но не всегда для ее подгрупп. So warning. Ну, просто вот как бы вот так. Ну, что вот это, вообще говоря, больше может быть. Ну, вот это вот алгебра Ли, которая отвечает за вычисление дифференциала, она может быть больше, чем алгебра, ну, настоящая алгебра Ли вот этого централизатора. Это как бы за счет, это из-за того, что вот когда вы тут считаете, ну, разницу между схемой и групповой схемой, вот когда вы вычисляете вот это m по m квадрату, вот это не равно, то есть это первое, что отличает, чувствует Ниль-радикал, что вот это не равно, ну, для h это не равно, ну, как бы вот разница между h и групповой схемой чувствуется на уровне, что m, ну, от h с волной по модулю mh с волной в квадрате не равно m от h по модулю m от h в квадрате. То есть как бы вот это больше, да?
Да, ну, а здесь получается, где GLV, мы просто можем сказать, что скобка Ли, она явно там в матрице.
Да, ну в смысле ну в смысле тут для двойственных, ну.
Поэтому все легко доказывать.
Да, а тут просто это явное вычисление просто за счет того, что у нас, ну как бы вот тут скобка это коммутатор, а тут скобка это, ну в смысле, что тут, so the proof of this thing is that here this is just centralizing is commuting, and here the centralizing is also commutation, but written in a different manner. Yeah? So this is because you have these direct formulas here. So I mean centralization here refers to commutation, and the derivation is precisely this bracket of this condition. And if you are looking in endomorphism, so saying which are commuting elements precisely, just yeah. So this is just a direct check. So and the problem is that in general there could be difference between group schema. But this is not the case for, so we are going to prove that in our case of semi-simple elements, we have still equality. So, the...
Не совсем понимаю, вот когда мы считаем вот эту штуку, да?
Да.
Если у нас группа, подгруппа в GLV, почему мы не можем считать опять, что коммутатор просто там, разность вот матриц, ну, как в GLV?
Не, ну тут же как бы одно плотно в другом, как бы, да, ну в смысле тут операторы плотны в обратимых, а когда у вас подгруппа, то у вас уже нет вложения их в свою алгебру Ли, из-за этого, ну, и получается проблема. То есть, ну, как бы это еще, ну, да, там происходит грубо говоря, что вот дополнительное условие — это пересечение с некоторым подмногообразием. Но вот когда вы делаете пересечение с многообразием, то ну вот тут как бы будет, вы должны взять одно является пересечением с приведенным, то есть разница между тем, что вы берете x и y, и вот что вы можете сделать? Вы можете посчитать алгебраическое пересечение между, просто вот как под схемы, so as a subscheme. And this calculation is this one. And you can do this calculation as a reduced structure. So here you can take the reduced structure of the intersection and take the tangent space.
Это наше определение стабилизатора, да? Потому что мы стабилизатор определяем как многообразие.
Но вот это вот есть ядро дифференциала, и вот это вот есть, so this is just a kernel. So if you can realize the intersection, so in our case, you can realize this intersection as the projection. Yeah, so you just you have the corresponding orbit morphism. Yeah. So you have this corresponding orbit morphism, and this H is which is the stabilizer, is just the kernel of the fiber. So it is just pre-image of the fiber over, if you think of the orbit morphism, yeah? So it is as the sub-scheme. So you should consider this as a sub-scheme structure. So you should consider this orbit map and consider H as with this sub-scheme structure. And this, if you think of sub-scheme structure, then this tangent space to H tilde is just the kernel of differential of df. So just by definition. And the reduced structure is smaller, so that just if you have reduced, reduced structure, then the tangent space will be smaller. So this is calculation in Lie algebra, because this bracket is related. So this is related with the calculation of differential, and actually, what you do, this was just one of the steps, so that how do you see precisely this differential? It appears as the differential of the following map. So we have considered this gamma S. So which is G S G inverse S inverse, and it is convenient to calculate the differential of gamma S from G to G. And the claim is that, so the proposition that now I shall use it, that this differential is obtained as 1 minus a joint action of S on G. Yeah. So here you have this map. You can consider the derivation in unit, and this derivation in unit is just equal to 1 minus, so a joint action on G. via this operator S, which is an element of G. And the claim is that, so this Lie algebra, so this this Lie algebra is just written in terms of the differentiable. So this is the kernel of such differentiable. So yeah, so we're also we're if so you can pick one element and you can pick up collection of elements. So here for GLV it doesn't matter. So the algebra. So if you have if you take some S as the subset in GLV in G. So for example, subalgebra. So the same for GLV, the Lie algebra of the centralizer of S is also will be equal to the Lie algebra of this element. And so maybe it is a good point to stop for today, since we have to do the break. So next time I shall be talking about the following picture. So the proposition that I'm going to prove, and it will be technical but rather short. That in fact that if S is semi-simple element, then the Lie algebra of the centralizer in G in H of S will be equal to the the corresponding Lie algebra of the elements. So the centralizer of so the elements in G that are the subalgebra in G in H that are centralized by S. Yeah. So this is just the elements of Xi of H such that a joint action of S of Xi is equal to Xi. And here, this is just the element, so Lie algebra of the centralizer, yeah? So that of elements of H, such that HS commutes with, so they commute together. So this is the claim that we are going to prove for semi-simple element. And out of this, I will derive that some properties of orbits. Yes, so I shall derive that orbits are in fact closed. Yes, so that just more important geometrical proposition that orbits of semi-simple elements are closed. So. Theorem, if S is semi-simple element of G, H normalize, the subgroup of G normalize S, then the set gamma S of H is closed subset. So in particular, all orbits of in a joint action of semi-simple elements are closed subsets. Yeah, so maybe at this point.